With mounting concerns over climate change, the utilization or conversion of carbon dioxide into sustainable synthetic hydrocarbon fuels, most notably for transportation purposes, continues to attract worldwide interest. This is particularly true in search for sustainable or renewable aviation fuels. This offers considerable potential, since instead of consuming fossil crude oil, the fuels are produced from carbon dioxide using sustainable, renewable hydrogen and energy. In a new discovery, fixation of carbon dioxide is made cheaper by converting it directly into aviation jet fuel using novel, inexpensive iron-based catalyst called FeMnK. This new catalyst can convert CO2 to hydrocarbons with a 38.2% yield, of which 47.8% is jet fuel. As this carbon dioxide is extracted from air and re-emitted from jet fuels when combusted in flight, the overall effect is carbon-neutral fuel. This contrasts with jet fuels produced from hydrocarbon fossil sources, where the combustion process unlocks fossil carbon and places it into the atmosphere in longevity as aerial carbon dioxide. For more than a century, our industrial society and humankind's prosperity, wealth and well-being have been based on the combustion of hydrocarbon fossil fuels. However, it is abundantly clear this has disturbed the natural environment by the emission of greenhouse gases, most notably from carbon dioxide, CO2, nitrous oxide, and methane. Nevertheless, the use of fossil fuels continues to grow with the expected annual increase of 1.3% to 2030, continually exacerbating this problem in the form of climate change. Air transport, playing a significant role in the modern world in worldwide social contact, business and marketing, is a recognized source of high CO2 emissions. Jet fuel, the generic name for aviation fuels used in gas turbine-powered aircraft, has as its main components linear and branched alkanes and cycloalkanes, with a typical carbon chain length distribution of C8 to C18, and where the ideal carbon chain length is C8 to C16. Given these recognized environmental concerns, it is now imperative to develop clean, energy-efficient technologies for producing sustainable or renewable aviation fuels. Converting CO2 into fuels and high-value added chemicals has attracted significant worldwide interest in the past few years, as it not only contributes to mitigating greenhouse gas emissions but also produces valuable chemical commodities. As such, CO2 conversion and utilization should be taken both an integral and important part of greenhouse gas control and sustainable development. Nevertheless, the activation of CO2 is extremely challenging. CO2 is a fully oxidized, thermodynamically stable and chemically inert molecule. Furthermore, hydrocarbon synthesis via the hydrogenation of CO2 usually favors the formation of short-chain rather than desirable long-chain hydrocarbons. Hence, most of the research in this area have focused on selective hydrogenation of CO2 to methane. The oxygenates methanol, formic acid, and light olefins, C2 to C4 olefins. There have been limited studies on producing liquid hydrocarbons of molecularity C5+. There are two ways to convert CO2 to liquid hydrocarbons: an indirect route which converts CO2 to CO or methanol and subsequently into liquid hydrocarbons, or the direct CO2 hydrogenation route, which is usually described as combination of reduction of CO2 to CO via the reverse water gas shift (RWGS) reaction and the subsequent hydrogenation of CO to long-chain hydrocarbons via Fischer-Tropsch synthesis (FTS). Jet fuel can then be obtained from the products after industrially recognized treatments such as distillation or hydroisomerization. The second direct route is generally recognized as being more economical and environmentally acceptable, as it involves fewer chemical processes, steps, and the overall energy consumption for the entire process is lower. The direct conversion of CO2 into fuels through these various reactions has attracted great attention in recent years. However, there are few reports of the direct catalytic conversion of CO2 to jet fuel range hydrocarbons. The key to advancing this process is to search for highly efficient and expensive catalysts that can preferentially synthesize the target hydrocarbon range of interest. Iron-based catalysts, widely used in both RWGS and FTS reactions, are typically prepared by chemical cold precipitation routes, which unfortunately consumes significant amounts of water. In this study, the preparation of iron-based catalyst was done using organic combustion method, OCM, and determined catalytic performance for the direct and efficient conversion of CO2 to jet fuel range hydrocarbons. In brief, the FeMnK catalyst shows CO2 conversion of 38.2% and selectivity to C8 to C16 hydrocarbons of 47.8%, with a correspondingly low selectivity for CH4 and CO. In addition, the process also shows a high molar production ratio of olefin to paraffin for C2 to C4 hydrocarbons. So how is it made? The organic combustion method, OCM, also known as the solution combustion method, was developed to prepare highly active metal catalysts for a variety of processes. The method combines a solution of required metal precursors as an oxidizing agent, which is iron nitrate nonahydrate, manganese nitrate tetrahydrate, and potassium nitrate, and a suitable organic fuel, which is citric acid monohydrate, as a reducing agent. This redox mixture ignites upon heating to initiate a self-propagating exothermic reaction that sustains high temperatures for a period of time sufficient to decompose all organic material. The final product is a crystallized material. Why use FeMnK? As said earlier, iron-based catalysts are widely used in both RWGS and FTS reactions. Meanwhile, manganese compounds are widely utilized as promoters of iron-based catalysts for FTS, where the addition of manganese typically improves activity, increases the surface basicity, and enhances the carburization of the catalyst. Another thing is potassium. The impact of potassium compounds on the performance of Fe-based catalysts for FTS has been studied extensively. Potassium is known to promote the formation of long-chain hydrocarbons, the carburization of surface Fe, and the suppression of CH4 formation, all of which are advantageous for liquid hydrocarbon synthesis. Lastly, citric acid. Compared to the catalyst prepared without organic fuel, all the FeMnK catalysts prepared with organic compounds generally showed a higher CO2 conversion and higher jet fuel range hydrocarbon selectivity. The catalysts prepared with EDTA, citric acid, oxalic acid, NTA, DTPA, tartaric acid, HEDTPA, and salicylic acid also exhibited good catalytic performance for both CO2 conversion and jet fuel selectivity. In general, all these organic fuels could also act as a chelating agent, and hence facilitating the formation of nanostructured catalysts. The resulting catalyst shows a carbon dioxide conversion through hydrogenation to hydrocarbons in the aviation fuel range of 38.2%, with a yield of 17.2% and a selectivity of 47.8%, and with the attendant low carbon monoxide 5.6% and a methane selectivity 10.4%. The conversion reaction also produces light olefins, ethylene, propylene, and butenes, totaling a yield of 8.7%, of which are important raw materials for the petrochemical industry and are presently also only obtained from fossil crude oil. So why do we need it? Renewable jet fuels offer considerable potential in the worldwide drive for the future sustainable circular economy future for the aviation industry. The vision centers on CO2 conversion as an integral part of carbon recycling. The advances reported here offer a route out of the current worldwide linear economy for jet fuels. Based on the present production, consumption, disposal, emission structure, where the valuable natural resource crude oil is extracted, shipped across oceans, transformed into jet fuel, and then combusted, with the combustion product either emitted into the atmosphere or trapped and buried underground through carbon capture and storage. On the other hand, the CE approach is based on the fundamentally different production, consumption, recycling, recovery structure, or the carbon capture and utilization. where, in this case, CO2 is indeed recognized as a powerful resource to be recirculated using renewable energy to yield carbon-neutral jet aviation fuel. This advance can contribute significantly to more sustainable fuel production processes if we input renewable energy into the chain for transporting CO2 into aviation jet fuel as an additional driving force for the inevitable and urgently required transition toward a circular fuel economy centered on renewable CO2 utilization. Within a jet fuel CO2 circular economy, the goods where the jet fuel are continually reprocessed in a closed environment, which saves the natural fossil resources and preserves the environment, whilst also of course creating significant numbers of new jobs, new economies, and new markets. The fundamental differences between the jet fuel linear economy as compared to the CO2 to jet fuel circular economy, where the entire latter process is a closed loop and hence a CO2 neutral process. This CO2 circular economy for aviation can surely empower the worldwide momentum toward not only major economic development for countries, but also achieving the UN Sustainable Development Goals.